Hello, I'm Michael O'Connell, and in today's video, we're going to derive expressions for pressure and temperature as functions of altitude. For this video, I would like you to consider a small pocket of air at a known altitude. What will happen to this small pocket of air as it rises? I think you would agree with me if I were to say that the pocket of air will expand. So, why does this happen? Hopefully, most of us have driven up to higher altitudes before and experienced the decrease in pressure, which actually decreases the amount of oxygen we're able to get into our bloodstream, which makes it harder to breathe. For our pocket of air, an expansion will occur. So, what assumptions can we make about this expansion that will make these derivations easier for us? First, I think we can say that, or we can assume, that this expansion is adiabatic, because air is a pretty bad thermal conductor anyway. So we would say that no heat is transferred from our system, which is the air pocket, to the surroundings, nor is any heat transferred from the surroundings to our air pocket. The next thing we can say is that the pressure inside the air pocket is the same as the pressure outside the air pocket. Basically, what we're saying is that this expansion happens reversibly, whereby the pressure inside our system is set equal to the pressure outside the system. Lastly, and definitely not to be forgotten, we're going to take the air to be an ideal gas. So, what I would like to talk about now is the basic equation of static fluids. So, we're going to have a differential change in pressure over a differential change in altitude is equal to the density, in this case of our air, multiplied by the acceleration due to gravity. So, that kind of begs a certain question of the sign, right? I remember always having trouble with that in physics. And it shouldn't be any trouble for us. We just need to figure out what direction is positive and what direction we want to be negative. So if we take increasing altitude, z, to be positive, then the acceleration due to gravity, the force that's going to be acting downward on our pocket of air, is going to be negative. Okay? So this can be negative rho g for the basic equation of static fluids. Okay, basically this is all good. The one thing we want to consider here is we have an ideal gas, so we can derive an expression real quick here for our density, right? The density of our air. What would that be? Okay, well, let's start with what we know. It's definitely mass per volume. We know volume from the ideal gas law, right? So that would be the number of moles times the ideal gas constant times the temperature, all of that divided by the pressure. So the pressure goes on top here in the numerator because it's a denominator in the denominator. Okay? And then what is mass per mole, right? That's going to be your average molecular weight of your air. Fancy M. That's like my favorite, one of my favorite variables to draw right there, if you were curious. This expression goes in there for density, and that is our expression for the basic equation of static fluids. Why is that important? That is important for us because we are trying to find expressions for pressure and temperature as functions of z, our altitude. And the expression that we now have for the basic equation of static fluids has pressure and temperature. This begs a new question that I would like to settle before we actually start deriving these expressions. And that is, what are we going to substitute in for? Are we going to substitute an expression in for temperature or pressure? The goal of the derivations we're about to perform is to relate the pressure and the temperature so that we can perform a substitution, then integrate and find one expression, and then use the previous equation, the relationship between the pressure and temperature, to find the other expression. Okay, so which one would we substitute if we find a relationship between pressure and temperature? Because we have the differential change in pressure in our basic equation of static fluids, we want to substitute in an equation for temperature, okay? Now, why would we want to do that? Well, let's think about what would happen if we substituted in an equation for pressure. That would create problems for us because we already have a differential change in pressure and a differential change in altitude here. on our left-hand side of the equation. Problem here is, when we go off to integrate, we have our temperature variable here. That's disastrous, because the temperature changes. That's not a constant. That would have to be in your integral. And then you wouldn't have the differential change in temperature as a part of that expression, and you would just get big red X's all over your paper on a test, and that would not be good. So that is why we're going to want to substitute in an expression for the temperature. So let's find what that's going to be. Okay, so we talked about how this rising pocket of air is expanding, right? And that happens adiabatically. That should hopefully remind you of the first law of thermodynamics, whereby we say that the change in the internal energy is equal to the heat added, subtracted from the external pressure, multiplied by the differential change in specific volume. Okay, this is zero, right? Because this is an adiabatic expansion. We also know that our system, the air pocket, is expanding. So the system is actually doing work on the surroundings. And for an adiabatic process, the change in internal energy is equivalent to the work done on the system. But this time, the work is being done on the surroundings, so the work done on the system is negative. This means that the internal energy decreases. Now, this goes back to that very important third assumption. This is an ideal gas for this derivation. That means for our internal energy, this internal energy change is only dependent on temperature. And this is good, because I just said the internal energy is going to decrease as we rise, or not we, but the air pocket rises in the atmosphere. And if it's only dependent on temperature, that means the temperature goes down. And that's good, because that's what I've experienced. When I hike up a mountain, like in Colorado, I get like extremely cold during the hike. The wind obviously plays a factor in that. But as you increase in altitude, the temperature will go down. Okay. Why is that the case? What expression should we recall here? Well, as I said, we have the change in the internal energy dependent on the change in temperature at constant specific volume. This expression here, in bad handwriting, that should ring a bell. And then this would have been multiplied by the differential change in temperature. This expression here, that's the specific heat capacity at constant volume, constant specific volume, that is. And we'll call that C sub V. Okay? So that's our left-hand side of the equation. Now, you can look at the right-hand side of the equation, and although we don't have any heat to worry about, you might be a little bit concerned about this PEXT, right? The pressure external. And you don't have to be, because we said that this process, this expansion of our pocket of air is reversible, which means that the pressure inside the air pocket is equal to the pressure outside. So we can denote that as P. So this is P dV. Okay, this is really good. Now, you see these two derivatives there, right? Differential change in temperature, differential change in specific volume. What does that mean? Well, that means that we need to treat this just like a separable differential equation, but we need terms with temperature and specific volume. We can get that from the ideal gas law, right? So that states that number of moles is not needed, right? Because we're dealing with specific volume. This is we could say some unit of volume, cubic meters per mole. Okay? So this is going to be what? RT over V, right? So that's what's going to go into our pressure. Okay, so let's rewrite that. Oh, one other manipulation I'm going to do. We have our differential change in temperature on this side, so let's multiply both sides by 1 over T. Okay, so we would have the constant there. This is constant, the specific heat at constant specific volume, 1 over T dt. And then we have the ideal gas constant R. Don't forget your negative sign there, divided by the specific volume dV. Okay, what are we ready to do now? We're ready to integrate. Now, whenever you're going to integrate, we also want to consider what are going to be our bounds of integration. So in the beginning of the video, I said that we're going to be considering for a model the pocket of air at a known altitude. We could call that Z sub 1. So we can say that we'll know the temperature and the specific volume of that pocket of air as well to start with. And then these, specific heat capacity at constant specific volume and the ideal gas constant R, those will come out of our integrals, right? Because they're constants. Okay? So we have that. T sub 1 is our lower bound, right? That's the temperature at that known altitude before our air pocket starts rising. And then I'm going to mark these variables with that dash there just to denote that they're part of the integrand there. And then this will be our unknown temperature, T, for our upper bound. So I'm just doing that to differentiate those so that we know that they're different so we don't get them mixed up. Okay? Now, this is negative. So a little bit of calculus knowledge here. We can flip those bounds of integration. Okay? So this upper bound is actually going to be the specific volume of our pocket of air at that known altitude. And then this is going to be the new specific volume at that higher altitude. Okay? Then we have 1 over V. Oh, forgot the R in front here. Okay. We know how to integrate this. This is very, very mild. Right? Natural logs. Okay? Let's divide both sides by R. What can we do next? Another cool property with natural logs, so if we multiply something against a natural log here, this becomes the exponent. What would that mean for us? Natural logs cancel. So that makes this look even prettier. We're using the ideal gas law, obviously, because we're dealing with this air that's an ideal gas. So we would say that V1 is equal to RT1 over P1. And then I'll just finish this fraction, right? So we would have that. Okay? So what would this expression look like now? The ideal gas constants cancel. And then we have the temperature at our known altitude there. And then we have this pressure. This is the pressure that we don't know, the pressure at the higher altitude. And this is a denominator in the denominator, so it becomes part of the numerator here. Okay, that's a good expression. Why is this a good expression? This is a much better expression than this because this is an expression that finally relates the pressure and the temperature. And as I said, we're going to want to substitute in for this temperature there. Okay, how can we do that? Well, we have this term here. So let's multiply both sides by T over T sub 1. So this would become a plus 1, right? Okay. All right. What do we do next? Well, again, we want to find something with the temperature equal to something else. Before we do that, I want to talk about this exponent here. This is something that we all need to know, okay? And that is this expression here. So the constant here would be the specific heat capacity at constant pressure is equal to the specific heat capacity at constant specific volume plus the ideal gas constant, or obviously for an ideal gas. Okay. How do we get that expression? Well, we get that expression because we have an ideal gas. We have the differential change in the enthalpy is equal to the differential change in the internal energy. And then normally we would have the pressure times the specific volume there. But again, we can make that RT This would be the differential change in the temperature there. We already know this, right? We already used that before. We know that this is C sub V dt. This, by definition, the enthalpy also will only depend on temperature for an ideal gas. And this is where you get the specific heat capacity at constant pressure dt. So as you can see here, boom, boom, boom. dt's go away, and you get that expression there. That's going to help us here with our exponent and just simplifying it a little bit, okay? So we want to make things easier, okay? And we would say that the specific heat capacity at constant specific volume divided by R. Let's make this common denominator whereby that be R over R. Okay, so this we already found to be the specific heat capacity at constant pressure. Okay. That is much easier for us to deal with because we're trying to find that expression for T, as I said. Okay, so we can raise both sides to the R over C sub P power, and then multiply each side by the T sub 1. So this becomes this expression here. And this is where you throw a big party with your friends. Because we got somewhere. A long journey, but we got there. And this goes into there. Okay? Just like that. So we're making that transfer. I'm going to take some time to erase this. And this is where someone like me who is very, shall we say, error prone when it comes to algebraic manipulations, as much as I enjoy this stuff, I make a lot of mistakes. So we have to be very careful. That's really the only remedy. So we have our expression here. And hopefully you're able to already kind of figure out without me telling you what expression we're going to find first. But we're plugging this in. This expression is in the denominator. Okay, so our T sub 1 will stay in the denominator. Let's write these. Now we have this pressure variable here and this pressure variable here. This is a numerator, though, in the denominator. So if we were to move it up here, it would be a denominator. Not a problem. It just means we can put this pressure term up there in the numerator and combine it with this other pressure term. We just need to flip the sign of our, of our exponent, right? This would be 1 minus R over Cp, I believe. Hopefully that's correct. Yeah, I'm struggling a bit with the algebra, but hopefully that makes sense, right? So we take the negative of this exponent, and we subtract it from this because this is raised to the first power. Okay, sorry, that should not have been as complicated as I made it. We can also move this, this P1, which is this is a denominator in the denominator, so it actually becomes a numerator by itself. So this would be P1 to the R over C sub P power as well. Sorry, try to delineate those. Those are different. Okay. And again, these are exponent. This is an exponent here. Really, really bad handwriting. And then we have the R and the T1. Okay. So I prepped you by saying I needed to be really careful, and I still choked on this part of the video. And for that, I'm very sorry. But I do believe what I've done is correct. So what do we want to do now? And I think I did reveal this earlier in this video. We have differential change in pressure, differential change in altitude. So we want this. You know, this is separable. We want this over here. Okay. That's maybe what was getting me confused. So this is where you can flip the signs on those, right? So we would have the pressure raised to the R over Cp value plus 1, okay? Oh, shoot, sorry, minus 1 dP. And then the rest of this big mess multiplied by dz. Okay, And don't worry, like, see, stuff like this, it's a constant, okay? So those will come out of the integral. So obviously the thing that we're going to have to do here is integrate. So now we're ready to continue. I wanted to take some time to erase and rewrite and do all of that stuff, kind of gather my thoughts a little bit there. And what do we need now? Of course, we need some bounds of integration. Okay, so I said z sub 1, that's the altitude that we know, and then the pressure that we know, p sub 1, and then I'll use those dashes again to mark those. Those are the variables inside of the integral. We don't want to confuse those with our bounds of integration. So this is the pressure that we're trying to find an expression for as it changes with altitude, and then this would be that new altitude for our pocket of air. Okay, so as you can see, this big mess here, that's a constant. That's outside of the integral there. We know how to derive this, right? So you would add 1 there. Thank goodness that goes away. And then you would divide. So this, you would divide by that, so you multiply by the reciprocal. So this would be c p over r, c sub p over r multiplied by p. And then obviously we would have our bounds of integration that we'd be plugging in there. And then this would still be raised to r over cp. So what I'm going to do before I plug in those bounds of integration is I'm actually going to throw this over to the other side. Notice that these r's are going to cancel. This would be division, so cp is going to go there. So if you don't mind me kind of just erasing and rewriting just to save space, that's what we're going to do there. I'm going to erase this now too so you don't get confused. But just remember what our bounds of integration were. So when we rewrite this, right? So this would just be, well, the unknown pressure at that higher altitude. And then minus the known pressure. Okay? Good. So we have that expression. What about this? Oh, this is super easy, right? So it's just the difference between z and z1. Okay? Nice. Okay. So what are we going to want to do now? Well, there's a couple things we can do. We want to isolate this pressure. Okay? So because that's our final answer. We want an expression for this pressure as it changes with the altitude z. So we can add this to both sides there. And as you can see, that would allow us to factor out this term. Okay? And with that, we should get something like this. So we would have r over c sub p there. And then let's see. So if we factored that out, I believe it would just be 1 because this would become positive minus our other terms here. Does that look right? Hopefully that's correct. Last thing we want to do, obviously, raise everything to the CP over R power on both sides. So this would go away. And then this would be the CP over R. And then just rewrite that. So we make it a little bit bearable if you're trying to write this down. And then that's our expression, magic. That is our expression for pressure as it changes with the altitude. So as you can see, the pressure goes down, right? By how much? Well, by this proportion, right? That giant messy thing. Okay, so we can actually get something very similar for temperature. I'm going to have to make a cut here so that I can get the expression that we had real quick. This is the expression that we had for temperature. So let's see what we can do with that, right? So if this is our expression for pressure, this is what we're going to plug in here. And then we're going to have an expression for temperature as a function of altitude as well. So again, if I didn't emphasize it enough already, like big square, big circle, like this is one of the expressions that we wanted to derive in this video. We're about to get the other one. So let's think about how we would be able to do that. So let me erase and give us some space here. Once again, we just had to be a little bit careful. And this is actually going to be beautiful, right? Because we have the reciprocal of this exponent. So those exponents are going to go away, which is awesome because they're just ugly, right? And then we have the p sub 1 in the bottom. So that's going to go away too. Because again, remember, this is what we're substituting. Excellent. So for that substitution, we have this expression for the temperature as it changes with the altitude. Okay? Excellent. All right, how does that look? That looks a lot better, right? No expression, there's nothing with the exponent in it. So I know this was probably a long video, and I tried to just do the best I could with the small whiteboard, but I really appreciate you watching, and I hope that this was helpful for you to see how we derive expressions for pressure and temperature as functions of altitude. So thank you so much for watching, and I'll see you next time.